Before we get into talking about the Pythagorean theorem and right triangles, we need to do a quick review over simplifying radicals, because when we take the square root using Pythagorean theorem, we're going to have to know what to do. What can we do other than using decimals in order to deal with our square roots? And sometimes we just simplify them, kind of like when we simplify fractions. So first, let's talk about what's a perfect square. If I talk about something that is a perfect square, 1 squared is 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and then so on. 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared. It's good to know through 15 squared just by heart. It just makes it a little bit faster when you're doing it. Now, when you do perfect squares, they're easy to take the square root of. So the square root of 25 is 5, because 5 squared is 25. So the square root of 36 is 6, because 6 squared is 36. And the square root of 100 is 10, because 10 squared is 100. And the square root of 49 is 7. So perfect squares and square roots, they come out with nice whole numbers. But what about the square root of 20? Well, the square root of 20 is not a perfect square. No whole number squared is 20, so it's going to be a decimal answer. It's going to be somewhere between 16 and 25. The square root of 20 is somewhere between the square root of 16 and 25, so it's somewhere between 4 and 5, because the square root of 16 is 4, the square root of 25 is 5, so the square root of 20 is somewhere in between. It's going to be slightly closer to 16 or just 4 than it is to 5. And if you type it in on your calculator, you get 4.472 and then a whole lot of decimals. The square root of 27 is going to be somewhere between the square root of 25 and the square root of 36. Those are the closest perfect squares to 27. So it will be somewhere between 5 and 6. It'll be closer to 5 than it will be to 6, because 27 is closer to 25. If you type it in on the calculator, you get 5.196 and then a whole bunch of decimals. Now, these answers are approximate, and it's really hard because we feel like they are, when I round, we feel like they're exact. But exact means all the decimals are included. We keep them. As soon as I say, nope, this answer is 4.5, I just said the rest of these numbers aren't important. That means that this is approximately 4.5. This is approximately 5.2. Okay? Exact answers mean that we want to leave the idea of all of the decimals. We don't want to do anything. We don't have to make a decision about what we're going to round to. So in order to do that, we're going to simplify the radical. There are two ways to do it. You can use perfect squares, or you can use factor trees. And I'll show you both ways. I personally prefer perfect squares. I think they're shorter, but I'll show you both ways. So using a factor tree, the square root of 24, we're just going to factor it. It becomes the square root of 2 and the square root of 12. Then that's the square root of 2 and the square root of 6. The square root of 2 and the square root of 3. Now what you're looking for is pairs, because the square root of 2 times the square root of 2 is 2. Okay, we talked about that before. The square root of 2 times the square root of 2 is 2. So these two, there's a pair. I can do the square root of 2 times the square root of 2 is 2. And then I have 2 leftovers at the bottom of the branches that didn't get used. The square root of 2 times the square root of 3 is the square root of 6. So that's with factor trees. That's one way to do it. You can also do it with perfect squares. Now, to do it with perfect squares, you'd go back up to this list and you'd say, okay, well, 24 falls right here. And so you work your way down the list. Does 16 go into 24 with a whole number? No. 9 doesn't go into 24 with a whole number, but 4 goes into 24. So 24 can be divided by 4. So what we would do is we would split 24 into its perfect square and its leftover. So 4 times 6 is 24. Now we just simplify from there. Take the square root of anything you know the square root of and leave the rest. I know what the square root of 4 is off the top of my head. It's 2. And then I don't know what the square root of 6 is. It's a decimal. I don't want to deal with decimals, so it's the square root of 6, and you just leave it. Both ways we got 2 square root of 6, 2 times the square root of 6. Okay, so it doesn't matter how you do it, whatever you want to do. Okay, again, like I said, I prefer perfect squares. So 27, go back up here. 27 falls right here. Work your way down the list. 25 doesn't go into 27 without decimals. 16 doesn't, but 9 does. So I break this up into the square root of 9 and the square root of 3, because 9 times 3 is 27. So I'm just splitting it into 2 pieces, or its factors. I know what the square root of 9 is. I can take that on the calculator. But the square root of 3 on the calculator is a decimal, so I'm just going to leave it all wrapped up in its nice little square root symbol instead of getting decimals. That is called leaving it exact. Okay, we are leaving our answers exact because I don't have to round. I'm not deciding that something's not important. The square root of 80, we go up here. Okay, then we just check. 80 divided by 64, divided by 49, divided by 36, divided by 25, divided by 16. 16 goes into 80, so we're going to split that into the square root of 16 and the square root of 5. Okay, the square root of 16 is a number I know. It's 4. The square root of 5 is a decimal I don't know, so I'm going to leave it alone. 4 times the square root of 5. 54, again, go back up to your list. That means you need to keep that list handy if you're going to use perfect squares. Work your way down the list until you get the biggest number, the biggest perfect square that goes into it, the square root of 9, and 9 times 6 is 54. The square root of 9 is 3. The square root of 6 is a decimal. I don't want to deal with that, so it's 3 times the square root of 6. Notice every time I have put the perfect square first. I do that so I'm being consistent. I do the same thing every time. Now, square root of 34. We go up here. 34 falls right here. 34 does not, 25 doesn't go into 34, 16 doesn't, 9 doesn't, 4 doesn't, and 1 does, but the square root of 1 is 1, so that doesn't help me any. So the square root of 34 is as simplified as it can get. So to leave it in exact form, I would just leave it alone. Okay, now the rest of these you can practice, so you can hit pause and then you can come back and check. But the square root of 18 is the square root of 9 and the square root of 2, which is 3 times the square root of 2. The square root of 125, if I reduce or simplify that, it's the square root of 25 times the square root of 5. The square root of 25 is 5. The square root of 5 is a decimal, so it's 5 times the square root of 5. Okay, 72. This one's tricky because we always want to go with 9 first, and that's okay. So what if you do that? What if you go with 9 first? Well, the square root of 9 and the square root of 8. Well, the square root of 9 is 3, and the square root of 8 is a decimal. However, recognize that 8 has a perfect square that goes into it. It's 4. So that'd be the square root of 4 and the square root of 2. But I still got this 3 hanging out here, right? I still got to include it. The square root of 4 is 2, so it's 3 times 2 times the square root of 2, or simplified, 6 times the square root of 2. Now, I could have made that a little bit easier if I had noticed. That's why I want to start up here and then work my way down the list, because if you work your way down the list instead of working up, you'll find out that 36 goes into 72, and the square root of 36 and the square root of 2, 36 times 2 is 72. The square root of 36 is 6. The square root of 2 is a decimal answer that we're not going to use, so my answer is 6 times the square root of 2. Notice you get the same answer. You just have to pay attention here that there's still more perfect squares. So 3 square root of 8 is just not simplified. That's the same as like taking, say, 4, or let's say 8 over 16, and reducing that to 4 over 8. Yes, we reduced it. We simplified it a little bit, but we're not all the way simplified, right? I could simplify that to 1 over 2, right? So we want to take it all the way down. We want to take out all the common things that they have. The square root of 180, if you find the biggest perfect square that goes into 180, it would be the square root of 36 times the square root of 5. The square root of 36, I know, that's 6. The square root of 5, I don't know. I'll leave it alone. So it is 6 times the square root of 5. So if you notice, like, look, so say this one right here, the square root of 125. The square root of 125 is approximately 11.2. Just to do a quick double check, 5 times the square root of 5 is also, see, they're the same. All we did was simplify it, just like we do when we reduce fractions. Okay? Now, how does that come about when we're dealing with Pythagorean theorem? First, let me remind you what Pythagorean theorem is. If you have a right triangle, then the square of the hypotenuse, which the hypotenuse is C, is equal to the sum, right, the addition of the squares of the legs. A is a leg, and B is a leg, and C is the hypotenuse. The hypotenuse is the longest side. It is directly across from the right angle. It's the largest side, the longest side, because it's across from the largest angle. Pythagorean theorem says a squared plus b squared is equal to c squared. The sum of the squares of the leg is equal to the square of the hypotenuse. That's what Pythagorean theorem says. So, some examples with Pythagorean theorem. Okay, solve for x. So you have to decide, every time you have to decide which is the hypotenuse. Always look for it. It's not always going to be on the same side. You can see all three of these triangles are rotated around where the right angle is in a different place. So in this case, here's my right angle, and here's my hypotenuse. Here's my right angle, here's my hypotenuse. Right angle, hypotenuse. Be careful, especially when they're looking like this. We always want to put them on the right-hand side or the left-hand side. Okay, so the two legs, a squared plus b squared. It doesn't matter which one is a and which one is b. I like my variable to be first if possible, so that's the reason I wrote it that way. Okay, so I would subtract 5 squared from both sides. You can simplify, but we can also handle this all at one time. Type it in your calculator. 13 squared minus 5 squared is 144. So x squared is 144. Okay, to fix that or to finish it out, we take the square root. So the square root of 144 is plus 12 or minus 12. We don't care about the minus 12 because I can't have a minus 12 or negative 12 as a side length. And so my side length then of the triangle would be 12. If this one, see we had a nice whole number, that was a perfect square, so it came out nice and easy. On this one, again, 10 is your hypotenuse, right? That's my C. It will be x squared plus a squared plus b squared is equal to c squared. Again, it doesn't matter which one's which. Now, if you do 10 squared minus 5 squared, you get that x squared is 75. Now, I need to point this out. It's not 10 minus 5 and then square it. Okay? It's not 10 minus 5 and then square it. It's 10 squared minus 5 squared. If you're going to do it all at once, you have to square it as you go. You can't do subtraction and then square. Order of operations says that you have to do those exponents first. Now the square root of 75, say you don't recognize it, the square root of 75 is a decimal. I asked you to leave your answer exact. That means you need to reduce your answer. Sorry, trying to keep it in focus that doesn't like the calculator. So we're going to go back to what we just did. The biggest perfect square that goes into, right, I need to take the square root. The biggest perfect square that goes into 75 is 25. It would be the square root of 25 and times 3. So 25 times 3 is 75. The square root of 25 is 5, and the square root of 3 is a decimal. So the final answer is 5 times the square root of 3. That's the exact, because I didn't have to round. I didn't have to do anything with the decimals at all. This last one, be careful, right? X is now your hypotenuse. So we're going to square these two sides. It doesn't matter which one's which. Be careful here. It's 2 square root of 3 squared plus 2 squared is equal to x squared. What I'm afraid that some of you will do is this, 2 root 3 squared. And you'll type that in on your calculator that way. Well, what happens is only the square root of 3 is getting squared, not the 2. So, right, you can pick up your calculator and let the calculator handle that math for you. 2 square root of 3. And then square it. And it gives you 6. Okay? Well, that's not right. So I know that's not right. So let me go back to square root of 3. Let me arrow out of this. Right? Squared. That's exactly what would happen if you just squared the square root of 3. You should get 12. Here's the reason I knew that was wrong. Because 2 squared is 4. The square root of 3 squared is 3, so I knew that had to be 12. 12 plus 4 is equal to x squared. X squared is 16, or if you take the square root of both sides, you get plus 16 or negative 16, positive 16, negative 16. We don't need the, or, excuse me, 4 plus positive 4, negative 4. We don't need the negative because we can't have a negative side length, so the only one we keep is 4. Now, one of the things that we have that's nice with Pythagorean theorem is there are certain things that happen all the time, and they come out nice and pretty. No decimals, kind of like this one right here. Those are called Pythagorean triples. They're very, very useful in construction, especially. For instance, this summer I was laying tile in my bathroom, and I laid out where I was going to start my tile, and I needed to make sure that it was a right angle. So I had these two lines, and I wanted to lay my tile right here in that first corner, but I need to make sure it's square at a right angle. So what I did is I measured 3 inches out and 4 inches out, or 5 because I needed a little bit more, so I did 6 and 8. So I measured 6 inches out, and I measured 8 inches up, and then I measured this diagonal. And if that diagonal was 10, then I knew that that was a right angle because of these Pythagorean triples. If you pull that up, there are so many videos on YouTube that show you how to use Pythagorean triples to check to make sure that your corners are square if you're framing a window or a door or you're building a foundation or something like that. Anything, lots and lots. It's used in trade a lot. Now, the most common families that we use in Pythagorean triples are 3, 4, and 5, or any multiple of that. So 6, 8, 10. 3 times 2, 4 times 2, 5 times 2. So that would also be your 3x, 4x, or 5x. So 9, 12, 15. Those are all multiples of your Pythagorean triples. So we have a 3, 4, 5, a 5, 12, 13 triple, an 8, 15, 17 triple, and a 7, 24, 25. I would say these two right here are the most common of all the ones that we use. And once we get past this unit, we'll be using Pythagorean theorem all year long. But if you look, a lot of times they're triples. They're meant to be a shortcut. So do you have to use them? No. But let me show you where it's helpful. For instance, this problem right here. I have this trapezoid. It has these two right triangle ends on them. It's an isosceles trapezoid because we have our two sides being 13 here and here. Right? And so I want to find x. Well, x is the entire bottom of the trapezoid. Well, I know that if this side is 9, this side from here to here is 9, because that's a rectangle, has those right angles in there. And so I need to find that other piece. Well, you can go through the math, and you can say, well, 5 squared plus x, or we'll call this y, right? 5 squared plus y squared is equal to 13 squared. Or you can go, wait, if that's 5, and the hypotenuse is 13, right? 5 is the hypotenuse, 13 is the hypotenuse, 17, the longest side's the hypotenuse. 5 and 13, if that's 5 and 13, that means this side has to be 12. I don't even have to do Pythagorean theorem. I just know this is 12 and this is 12. I didn't have to do anything. You can, if you get stuck and you don't remember, you can always go back and do Pythagorean theorem. But there is great benefit to knowing those Pythagorean triples. They're really a time saver, especially on PSAT, SAT, ACT, stuff like that. So 12 plus 9 plus 12 is 33. So the length of that side is 33. Number 5, the problem is I want x. The problem is if you look at x, that right triangle doesn't have enough information because I don't have this side. And to use Pythagorean theorem, you have to know 2 of the 3 sides. This big triangle is not a right triangle, so I can't use Pythagorean theorem on it. But I do know that this is, because that's a linear pair, so I know that's a right triangle. So if I look at this one right here, here's what I notice. I notice that one side is 6 and one side is 10. Right? You can carry on and you can do Pythagorean theorem all day. That's fine, no problem. However, I notice that this is a multiple of 5 and this is a multiple of 3. So I just need to make sure they're the same. This is 3 times 2, right? This is 3 times 2. This is 5 times 2. Well, if I know my triples, then I recognize that this is a 3, 4, 5 multiple. That means this is 4 times 2, or 8. So I already know, without having to do a whole lot of math, that that side, that leg of the triangle is 8. Now it's 8, 12, and then whatever this number is. Well, let's check and see if this is a triple. Well, this would be 4 times 2, and this was 3 times 4. So these are not multiples of 3 and 4. They're not multiples of any of the other ones. So this is not a triple. So I could use it here, but I can't use it here. So sometimes you have to use Pythagorean theorem, but sometimes you don't. This would be 8 squared plus 12 squared is equal to x squared. You get that 64 plus 144 is 208, right? Find the biggest perfect square that goes into 208, and you get 16. So the square root of 16, and 16 goes into it 13 times. The square root of 16 times 13, the square root of 16 is 4, and the square root of 13 is a decimal. It doesn't come out pretty, and so it's 4 square root of 13. And so the answer then is 4 square root of 13 if we leave it exact. That's exact. You've got to understand the difference between exact and approximate. 4 times the square root of 13 is 14 point. But see, look at all those decimals, right? As soon as I say 14.4, that is not approximate. I mean, that is not exact. That is approximate because those numbers exist, and as soon as I cut them out, I've made it not, right? This is what I call a NASA number. If they're going to send me to the moon, that's the number I want them to plug into the calculator. If I'm just going to Home Depot and I just need a roundabout, right, I'm going to go with 14.4, even though it was 14.42. I might even round up to 14.5 if I'm going to Home Depot to buy a board, right? But this is approximate. Please know the difference. All right, this last one. Find the perimeter of triangle ABC. So one of the things, notice that this is on a grid, and the nice thing about it being on a grid is we can start to use Pythagorean theorem instead of the distance formula. Well, we need to turn this into a right triangle. This is not. So what I want to do is to find AB, I'm going to use this little pink triangle right here because the hypotenuse of that pink triangle is the side that I'm looking for. AB, so I would go up 5, and it goes over 12. Well, I notice that's a 5, that's a 12. That means there's a Pythagorean triple. So without having to do Pythagorean theorem, I automatically know that AB is 13. Never had to do a Pythagorean triple, or never had to do Pythagorean theorem. It's a triple. Use them when you can. And then I want BC. So if I want BC, I'm going to draw in this right triangle right here so I can see it. BC is my hypotenuse. One leg is 3, one leg is 4. Well, that's 3, that's 4. That means the hypotenuse has to be 5. Let me point out one thing. Be careful here. If this is 5 and this is 3, this is not a 3, 4, 5 triangle. Okay? This 3, 4, 5 doesn't work because the 5 has to be on the hypotenuse. Because this can't be 4. The hypotenuse can't be shorter than one of the legs. So if it's this way, right, if it looks like this and the hypotenuse is not the longest side and it's not a 5, then you can't use the triple. You have to do Pythagorean theorem like you always do. Doesn't always work. Pythagorean theorem doesn't always work. Then this last one, I want AC. AC is the hypotenuse of this right triangle right here. This has a side length of 2 and a base of 16. Double check that. 2, 4, 6, 8, 10, 12, 14, 16. Yes. Now, that's not a triple. There's not anything with a 2 and a 16. So in this case, you do actually have to do Pythagorean theorem. Let me write this down. BC was 5. So then Pythagorean theorem, 2 squared plus 16 squared is equal to, I'll just call it x squared. You can call it c, whatever you want. 4 plus 256 is 260. 260 is equal to x squared. This time we're going to, we'll go ahead and round it so that we can actually get the perimeter and add them together. So the square root of 260 is 16.12. Right, if you type that in, square root of 260. Okay, it's all those decimals. I rounded it, so that's approximately 16.12. And add that together, 16.12, you get that the perimeter is equal to 34.1. So these triples are very, very important. Take the time to memorize them. There are more, but at least know these two. Okay? They're extremely important and they're very, very useful. Pythagorean theorem is a squared plus b squared is equal to c squared, where c is the longest side of the hypotenuse.